We're going to look at data transformation, and in data transformation one applies a mathematical manipulation to each score. Here are some examples of data transformation. Transforming all scores to z-scores, adding a constant to each score, multiplying each score by a constant, squaring each score, taking a square root of each score, taking the log of each score, computing each score's reciprocal. Suppose you have the combination of very small sample size and very high skewness for your distribution. As talked about in the prior video, one strategy is to conduct a non-parametric alternative test to the parametric test that would otherwise be conducted. As you know, the parametric test could yield inaccurate results due to the combination of small sample size and very strong skew. Another strategy is to transform the dependent variable so that its shape becomes close to normal. So consider the behavior problem scores in Group 1 and Group 2. Within each group, these scores are ranked from low to, well, they're not ranked. I mean, they're ordered from lowest score to highest score, and you can see that within both groups we have positive skew. That is, that the scores are more spread out at the higher end and, relatively speaking, more clustered or bunched at the lower end of the distribution. So here we have box plots of scores in Group 1 and Group 2, and the greater spread of the boxes upwards of the line in the middle of the box is conveying the median score. The boxes are more spread out in the upwards or positive direction. That conveys positive skew. So also does the greater length of the positive whiskers than the negative whiskers. So here, for instance, is one of our positive whiskers, and the negative whisker is much shorter. And again, that's conveying positives. So conducting an independent t-test in this situation could yield inaccurate results. Now let's go ahead and implement a square root transformation. We'll take the square root of each score, and those will become our new scores, and let's plot those square roots using the box plot. And so here are the scores in Group 1, here are the scores in Group 2. I mean, more specifically, these are the square root of the scores, and you can see now that in both groups within the boxes are spread approximately equally above and below the line in the middle, which is the median, and further the whiskers are reasonably equal in length. So these box plots now are conveying to us distributions that have only a modest amount of skew. So these distributions are much closer in shape to a normal distribution than was the case prior to transformation. But the gist of the matter is, because skew now is quite modest, an independent sample t-test will now yield a quite accurate value of p. And I experimented with this data. I carried out an independent samples t-test on the raw scores, that is to say on the scores prior to transformation, and the p-value from the t-test was 0.158, and that value is suspect due to the combination of very strong skew and very small sample size. Now, subsequent to transformation, that is for the square roots, I again carried out the independent samples t-test, and the probability from that test is 0.219. So we can have much more confidence in that probability because the distributions are no longer strongly skewed. Second p-value is almost assuredly more accurate. Now, I mean, as I mentioned, another alternative in this situation would have been to carry out a non-parametric test. The Mann-Whitney U-test is the preferred non-parametric test in this alternative, and I carried out a Mann-Whitney U-test, and it yielded a p of 0.281. And as you know from the prior video, the Mann-Whitney U-test doesn't work on the actual scores. It doesn't use the raw data in its calculations, but rather it uses the ranks of the behavior scores. Now, both the data transformation to markedly reduce the skew and to make the distributions fairly close to normal, and the Mann-Whitney U-test, both of these are good options in this situation. I note that it's much more common to encounter positively skewed data than negatively skewed data, and square root and log transformations are often good options to reduce the skew of positively skewed data and therefore render these distributions closer to normal in shape. We want to talk a little bit about single case designs. In a single case design, measurements are taken on at least several occasions, both prior to and following an intervention. We're only going to talk about one of the various simplest single case designs, and that is the AB design. So the A phase of the AB design is the baseline phase, and the baseline phase consists of the pre-intervention observations. The B phase is also termed the intervention phase, and it consists of the post-intervention observations. So I think it's helpful to think of the baseline phase as a control group and the intervention phase as an experimental group. So let's suppose that we have a single case design, a simple, straightforward AB design. What we're going to be doing is having a parent count the number of times that she or he nags their child. And so we're going to take, let's see, 1, 2, 3, 4, 5, 6, 7, 8 baseline measurements, and then we are going to intervene. Perhaps some kind of a behavior modification regimen is set up, or perhaps something different. Perhaps some time to relax and de-stress is made for the parent. So here are the number of nags in the post-intervention phase, which is to say in the B phase, or in the intervention phase. Well, let's take a look at this data. Here are our baseline measurements. The vertical line in the middle conveys the time of intervention. We can eyeball this data, and you can see the baseline measurements are higher than the intervention phase ones, so there is indeed a decline, at least visually, from baseline to intervention. Now, though the baseline phase went up and down a lot in the prior slide, is to say, though it fluctuates considerably, the overall trend was the absence of a trend. In other words, overall, the line was, if you drew a line through the dots of the baseline phase, that line would be roughly horizontal. The baseline measurements were not trending upwards. That would be indicated by a pattern sloping from lower left to upper right, and similarly they weren't trending downwards. That would be indicated by an upper left to lower right pattern, but rather the overall trend was horizontal. So here's what I mean. We could draw a line through the baseline phase, and that line is roughly horizontal. It's not trending upwards. It's not trending downwards. There's a lot of fluctuation, but overall our pattern is a horizontal one. Now, if you see a baseline that does have a strong upwards or downward trends, then the significance test that I'm going to describe here would not be appropriate. Well, what test should we use here? We've got two groups, a baseline group and an intervention group. The baseline phase and the intervention phase, we've got a numeric dependent variable. So this would suggest that an independent samples t-test would be a good alternative. And indeed, an independent samples t-test would be an acceptable alternative. However, the sample size at 8 in each group is awfully small, perhaps too small for a t-test. So given the very small sample size, I might tend towards a Mann-Whitney U-test. So we could go ahead and carry out a Mann-Whitney U-test, and that would examine whether the observations in the baseline phase were higher or lower versus the intervention phase. And remember, it's dealing with ranks rather than with the numeric data per se. So the Mann-Whitney U-test was indeed significant. We would reject the null. So the change in nagging from baseline to intervention is unlikely to be due to chance alone. Our dependent variable in the prior single case design was numeric. What if we have a categorical dependent variable? Let's use a dichotomous dependent variable. So our dependent variable is going to be, does our client participate, yes versus no, in socialization activities? So we find that at baseline, the client participates on 2 days out of 12. In intervention, the client participates on 10 of 15 days, and we're up from 17% participation to 67% participation. Now, what test would we use? I mean, we've got categorical data here. We've got two variables. I mean, one variable is, are we in baseline or are we in intervention? That's our independent variable. And our second variable, the dependent, is participation, yes or no. So a chi-square test would be a good choice here. For sufficiently accurate chi-square test results, we need our average observed frequency to be greater than 6. So we have 25 observations. We have 4 cells in our chi-square example, 4 cells in the crosstab table. So dividing 25 by 4, we get 6.25, and that is indeed greater than 6, so we're okay. From that perspective, for chi-square results to be accurate in a 2 by 2 table, we also need for the minimum expected frequency to be greater than 1. I don't show the calculation of the expected frequencies here, but the expected frequency in the upper left cell was the smallest expected frequency, and it calculated to 4.8. Well, I guess we do show the calculation. 12 times 10 divided by 25 calculates our expected frequency of 4.8, and that's greater than 1. So we can go ahead and carry out our chi-square test, and the chi-square test results here are presented in the form that they would appear in a journal article. So chi-square with 1 degree of freedom. The degrees of freedom are -1 times c minus 1, number of rows times -1 times number of columns -1. The row size is 2, the column size is 2, so 2 minus 1 times 2 minus 1, 1 times 1 equals 1, sample size of 25. The chi-square is 5.235. The computer software package calculates the exact p. It's a non-directional p, and the 0.022 is less than 0.05. We'll presume 0.05 to be our selected significance level, so we reject the null. And we would conclude that the difference in baseline and intervention percentages with respect to days socialized is unlikely to be due to chance alone. Some comments on single case designs. I mean, sample size is often small, therefore power is often low. So sometimes you fail to reject the null due to low power. Single case designs are classified as quasi-experiments. We don't have random assignment to groups. And because we don't have random assignment to groups, it is difficult to know, and indeed almost always we can't be confident that a statistically significant difference is indeed due to the intervention. So just as an example, in the prior example, we saw greater socialization in the intervention phase than in the baseline phase, and the baseline to intervention difference was a statistically significant one. It might be that some other factor came into play. So we intervened to increase socialization, but perhaps there was a major life change that took place at about the same time. So that, rather than our intervention per se, might be the cause of the difference. So the degree of causality in single case designs is not equal to that of randomized studies, but on the other hand, oftentimes it can be better than the causality that one finds in a survey. Well, what is serial dependency? Serial dependency in a pragmatic sense is the problem that observations that occur close together in time may have more similar values than do those that do not occur close together in time. So if you have serial dependency, you're violating the independence of observations assumption. In essence, observations that occur close together tend to be more similar than to those that occur farther apart in time. And in a situation like this, the standard straightforward statistical significance tests that are presented in this text can yield inaccurate results. So here's an example of a string of data where we've got serial dependency. Y conveys participates in socialization. It stands for yes. N conveys does not participate. So look at the streaks, the clusters here. First we get 5 N's, and then 3 Y's, and then 2 N's, and then 7 Y's, and then 3 N's, and then again 5 Y's, and so on. So these data are occurring in streaks, and it looks to me like this data is not serially dependent. So what we can do is carry out a significance test to see if the independence of observations assumption is violated. In other words, to see whether we've got serial dependence. So we can look at this data in the format of a crosstab table. So we're listing the prior observation as our column variable. So if indeed a preceding observation, if indeed the immediately prior observation was yes, participate, then 81% of the time, that is 13 out of 16 cases, subsequent observation was yes, participate. But on the other hand, if the prior observation was no, did not participate, then the subsequent observation was yes, precipitate in only 4 of 14 cases, that is 29% of the time. So where the prior observation is yes, 81% of subsequent observations are yes. Where the prior observation is no, only 29% of subsequent participations are yes. I mean, this should be yes. So I've corrected the mistake. Where the prior observation is no, 29% of subsequent observations are yes, and that's this cell here. Okay, so the difference in percentages saying yes at the subsequent observation time is 52%. That's a strong relationship, and indeed I carried out a chi-square test for the data in this table, and the chi-square test p-value was 0.004. So this is telling us that there is a statistically significant association between prior observation and subsequent observation. It's in essence telling us that there is indeed serial dependency. If you have serial dependency in your data, such as is the case in this particular example, then your tests of baseline versus intervention differences may be inaccurate. So you have to be alert to the possibility of serial dependency. If you've got serial dependency, you've got to use a significance test that's much more complicated than those presented here. And it is very difficult to know whether you've got serial dependency because, usually you're dealing with a small number of observations in single case design. So this is a tricky issue. I think the best pragmatically you can do is go ahead and carry out your appropriate test of the pre-test, post-test difference, and then as you write up your report, you might write out that one should consider the possibility of serial dependency in interpreting the findings. Now, the example that we were just looking at was demonstrating serial dependency for a categorical variable, that being yes participated versus no did not participate. Now suppose you had a numeric dependent variable. Well, then what would serial dependency look like? So the bottom here is showing us, I suppose, days. This study presumably takes place across about 46 days, and what you see is a serpentine or snake-like pattern. So here, for instance, are about 8 or 10 data points, all of which are high in value. And then here is a group of 4 or 5 that are low. So we're not seeing a random bouncing sort of back and forth across this line that cuts across the middle, but rather we're seeing highs tending to go together in time and lows tending to go together in time. So if you see a pattern like this, you've got possibly serial dependency for a numeric dependent variable, and in a situation like this, either a independent samples t-test of the pre-intervention, post-intervention difference, or perhaps you'd do a Mann-Whitney U-test instead, but at any rate, those tests will not yield accurate p-values if you have serial dependency. There's a footnote in the text that speaks to serial dependency for numeric variables, but basically it's a fairly complicated issue, so I think you just go ahead and carry out the t-test or other test, and then note in your report that serial dependency may be affecting the data.